So we'll go ahead and get started. We will continue with the NMR for proton NMR. We talked about identifying particular groups, which ones are unique, which are equivalent. And also we looked at chemical shift, determining, depending on the environment it's in, where we expect the various regions to be for the spectra. The next thing we're going to be talking about is some integration. The number of hydrogens is directly proportional to the size of the peak that we see in a spectrum. So if one peak is twice the size of another, it means it has twice as many hydrogens. So here we're talking about the number of equivalent hydrogens giving rise to a peak as opposed to the number of different types of hydrogens. For compounds such as this, it's important to remember that we are looking at relative amounts. If we look at the integrations that are underneath this, we have 32.5 and 48. Divide each of these by the smallest. We set this one to 1. We do the same here, and we get 1.5. Of course, we can't have 1.5 hydrogens, so we would double these and say it's a 2 hydrogen to 3 hydrogen ratio. And that does give us the relative amounts. But this compound, remember we've got that axis of rotation down the center, so the left and right halves are equivalent. So really we have a 4 to 6 ratio here. The NMR doesn't give us that information, it just gives us the relative amounts. And to get absolute, we would have to have something like the formula that's given here to be able to get that, or some other reference to know this is indeed 1 or this is indeed 2, and then we could get absolute amounts. But the integration does give us relative amounts for each of those. One thing you've probably noticed is that when I talk about peaks, oftentimes it is not a single peak, but the peaks are split. So we have these different patterns: singlet, doublet, triplet, quartet, quintet, sextet, septet. And then we would have octet and nonet as well in that list. And basically it's giving the number of peaks that we see, although the pattern is very specific as well. This is a result of something we call splitting or coupling, where two hydrogens that are near each other, bond-wise, typically 2 to 3 bonds, one will split the other. That comes about, if you remember back when we first talked about NMR, when I first introduced the topic, we said we drop the nuclei into some magnetic field. This would be our B0 field. That the nuclei act like little magnets, where some of them will line up with that field, but others will line up opposed to that field. And the number is going to be greater for the number that are lined up with the field. It's a lower energy state than those that are opposite, but the numbers are very close. They're nearly equal. So when we look at hydrogen A here, it's going to have a hydrogen B, and that hydrogen B will either be lined up with it or it's going to be opposite. If it's lined up with it, since it's also acting like a little magnet, it's going to amplify the B0. We've got that applied field. Of course, this thing's going to add a tiny amount, but it is going to add a small amount of magnetic field intensity to it. So if our HA all by itself appeared here, because we are now adding a slightly greater field, we are in effect de-shielding that magnet, so we're going to have the peak moving to slightly greater chemical shift. On the other hand, if B is opposite, now we have a magnetic field that's opposite B0. It's going to make B0 slightly weaker, or at least the field that the hydrogen A is experiencing is going to be slightly weaker, and so it's going to be at a slightly lower chemical shift. And of course, when we do NMR spectroscopy, we're not analyzing a single molecule where we have just one A. We've got a whole bunch of them there. Depending on what you've put in, we're talking billions or trillions of them. And so half of those are going to have spin up for hydrogen B, half of them spin down. And so we're going to end up with 2 peaks of equal intensity. And that's what gives rise to our doublet. It's because of the other hydrogen either being spin up or spin down, either adding to the B0 or subtracting from it. And so we get a doublet like that. If we have two hydrogens, so now we have two HBs, same thing's happening. We've got our HBs, except now we've got four different orientations for the hydrogen B. They can both be aligned with the field, in which case we are again increasing the B0. So again, if we say that our typical HA would be here, by having two of them, we're increasing the shift, and we get a peak that's at greater chemical shift. But we can also have one hydrogen up and the other down, or down and up. In either case, those two magnetic fields from the other nuclei are canceling each other. And so then the hydrogen A will be experiencing exactly the B0. It doesn't change. And then if they're both down, again, we're seeing a shift where it's decreasing that. And because this is a statistical distribution, we'll have 25% like this, 25 here, 25 here, 25 here. But these two are the same, so basically it's 50% are going to give that center peak. And so for the triplet, we always end up with a 1 to 2 to 1 ratio. And so because those outer ones, we have half as the population we do the inner, where we have either up, down, or down, up. Okay. Same applies to the quartet, except now we have a total of 8 different orientations. But again, we're seeing the same thing. These are increasing the shift. 2 up and 1 down, we're going to have a smaller increase, but still increase, a small decrease and a larger decrease. And so we'll see 4 peaks. And again, because of this distribution, it will be a 1 to 3 to 3 to 1 ratio. And so this would be our quartet. And so we have this pattern then that's forming in our splitting due to the neighboring hydrogens. We have, jump one more here. So this is the basic pattern we're seeing. This is Pascal's triangle, if you don't recognize that from your math class. But if we take this to the next level, it would be 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and then 1. So the quintet is a 1, 4, 6, 4, 1 pattern. And we can see those on down. Septet, and if you want to know octet, you would just add them together. It'd be a 1, 7, 21, 35, 35, 21, 7, 1 pattern. And put this one in the back of your minds. We're going to be revisiting that in a few more slides, but you don't need to memorize it for anything. Just keep it in the back of the mind. But this does also give us out what is referred to as the n+1 rule. If the hydrogen has one neighbor, we're going to have a doublet. If it has 2 neighbors, we get a triplet. 3 neighbors, we get a quartet. So the number of neighboring hydrogens is going to be 1 less than the number of peaks. Or n+1, the number of peaks is 1 greater than the number of neighbors. And so we can actually use that to try to assemble pieces when we look at our spectrum to see what is bonded to what. For the splitting to occur, we typically see this only for 2 and 3 bond relations. So we've been looking at examples where we had A and B on adjacent carbons or vicinal. This is a 3 bond coupling. We do see it for 2 bond, where the 2 hydrogens are on the same atom, provided they are unique. If these 2 hydrogens are equivalent, we do not see any splitting. So we would only see it if those are unique hydrogens. And then those 2 would split each other as well. We generally do not see it for 5 bond or greater. There is an exception with the 5 bond. We do see that if that's a 4 bond coupling. We do see it in the 4 bond coupling if all 5 atoms are coplanar. All 3 carbons and both hydrogens are all in the same plane. We will see that, which largely restricts this. I'm going to put that here. 5 atoms coplanar. And we see that in aromatic systems. Sometimes you will see it in bicyclic systems where you've got 2 rings that are fused together that hold it rigidly and specifically so that they're all coplanar. You don't see that a whole lot outside of aromatics. And if it's a big floppy molecule, you won't see that. So long chains, we don't see the 4-bond coupling. Right. This does apply, it says here, I'm going to change this, the n+1 rule only applies to protons that are all equivalent. I'm going to strike that equivalent and put that have same coupling constant. And we'll talk about what a coupling constant is in a few slides, but I apologize for my writing, but I find if I rest my hand on the screen, it does weird things. So hydrogen A here, or I guess we only have the 1 hydrogen, this would not be a triplet even though it has 1 neighbor here and 1 here. Normally we would think 2 neighbors, a triplet. The reason is that the splitting from these 2 are going to be different. And so it's not going to give that nice triplet. It's going to give a pattern called a doublet of doublet, which will be discussed later. But so if you have very different systems like that, we can get different splitting, and we don't get the nice patterns that we're looking at, and we don't see the n+1 rule. But generally, if you have floppy chains, so if we look at something like propanol, and this would apply to a longer chain as well, but I'm just going to keep this one short for now. This CH2 here, this has 2 neighbors. So this is going to be a triplet. Likewise, our methyl out here, it's next to a CH2, so this is going to be a triplet. This one has 2 neighbors on one side, 3 neighbors on the other. So it's going to be a quintet. It will be split into 5. So the n+1 rule is applying, and it would apply if we had a 4-carbon chain, 5-carbon chain, whatever. It's a big floppy molecule. This would still apply even though these are not equivalent. Methyl and methylene are definitely can't be equivalent since there are different numbers of hydrogens on those carbons. But we still see that same n+1 because they will have similar coupling constants. Yes?
So that methylene in the middle, it has 3 neighboring hydrogens, correct?
This one has 3 on this side, 2 on this side. So it has a total of 5. And I know exactly where you're going. That should be a sextet. Thank you. 5 neighbors, n+1 would be 6, so this should be a sextet. Thank you for catching that. Right. So the n+1 rule applies for big floppy chains. As you start putting it in rings or adding double bonds, things that make it rigid, that n+1 rule will fall apart for the things near the ring or on the ring or on or near that double bond. As you get away from it, it starts applying again. Okay. So we'll look at, this is an example, asks to predict the splitting patterns for the protons in the molecule below. Of course, the first step is to identify the hydrogens that we have and which ones are unique and equivalent. So we definitely have CH3 here. We also have CH3 there. We have a hydrogen here. As far as those methyls, because they are in this isopropyl group, we have rotation around this bond, and we do not have a chiral center, so these will be equivalent. It'd be no different than having 2 hydrogens on a methylene, methyls on the same carbon. If they're equivalent like that or identical in that respect, if you don't have a chiral center, they will be equivalent. So we could call these both HA, and they're both going to be doublets. Hydrogen B has a total of 6 neighbors. It's got 3 in the above methyl, 3 below, so it's a total of 6. Makes this a septet. And common convention for NMR, when you talk about singlet, doublet, triplet, And quartet, you can use the one-letter abbreviation, the S, D for doublet, T for triplet, Q for quartet. Anything above a quartet, you spell it out. Obviously, quintet, we can't use the Q because we've already got that. Sextet, septet, we've already used the S, we can't use that, so we have to write it out. There's no hydrogen on that carbon, but there is one here. So we can call this hydrogen C. We've got two more here. Question is, are those equivalent? Remember, the rule is if they're on the same carbon, that methylene, those hydrogens are equivalent unless we have a chiral center, which we do not, so that would make these two equivalent to each other. And hydrogen C would be a triplet. It has two neighbors. Those hydrogen Ds are the two neighbors. Hydrogen D, on the other hand, they have one neighbor, so these would be doublets. Because remember, the equivalent ones don't split them each other. And so these two do not split each other because they are equivalent. If they were not equivalent, they would split each other as well. And we will see an example of that. And then we have the two vanillic hydrogens, call them E and F. And both of these will be doublets. They will split each other. But they're far enough away that they're not split by D. Remember, we're limited to basically a 1, 2, 3 bond. Here we've got something else in between. This would be a 1, 2, 3, 4 bond, and we don't see that splitting. And so the next slide shows that a little more neatly. It's all typed there. Also expands the hydrogens to show clearly that we have 6 explicit HAs there. So that would be the splitting that we would see for each of those. Comment on, and we're getting here to the coupling constant, the J value, but when we see splitting between two different hydrogens, so hydrogen A on the one hand, hydrogen B, when they split each other, they're going to split with the same coupling constant, which means they're going to have the same distance between these two peaks. Any adjacent peaks in the multiplet are going to be equally spaced, and that distance between those peaks measured in hertz is the coupling constant. So if this distance measured in hertz, if that is 10 hertz, make my one a little more clear. So 10 hertz between those, that means the other ones are also going to be 10 hertz. We will have 10 hertz between these, and again between those. But this is also true for whatever is splitting it, it splits the other. If A splits B, B will also split A. And so these will also be 10 hertz. If they're not equal, then they're not splitting each other. So this would also have to be 10 hertz. And the coupling constants are always hertz. They're called a constant because it is constant in hertz. If you have a particular molecule, say ethanol, and you have an 8 hertz coupling between two peaks, doesn't matter which instrument you collect spectrum on, doesn't matter what the magnetic strength is, the coupling is still going to be that same 8 hertz for every instrument you collect the spectrum on. And the ppm difference will change because of the strength of the magnet, but the hertz does not. This is another example. They're bringing it up. The top one, we have equal spacing between these and these. And so we can assume that these two are probably splitting each other. This would not be an example of an ethyl group for a couple of reasons, but one of them is the fact that the distance between this peak is much greater than the distance between these. And again, if the coupling constant between the two multiplets are different, they're not splitting each other. There's something else that's causing this triplet, not the hydrogens here. And there's something else causing this quartet. You've got a CH3 somewhere that is certainly not this one, even if this integrated to 3. Yes?
What exactly is happening when hydrogens are splitting each other? What does that mean?
It's what I talked about at the very beginning of the presentation, with the hydrogen on the adjacent atom being in opposite orientation. That's causing the hydrogen for one molecule being at a different chemical shift than the other one. And it's because of the orientations. And so we're saying that one signal we would expect to get is being split into two, or to three into whatever. And so we call that the splitting. The other reason this would not be an ethyl group, of course, is the fact that for ethyl you have to have a 2-hydrogen to 3-hydrogen ratio. We don't have integrations here, but obviously this is a very big peak, so the area under this is certainly greater than here, not 2/3 of this one. So an ethyl group, it's a common group that you're going to see, so you should kind of have it in the back of your mind that if you see a triplet and a quartet in a 3-to-2 hydrogen ratio, you should think ethyl. And then you can check to make sure the coupling constants are the same, then they probably are. If they're different, then it's probably not an ethyl. Yes?
Does that mean that the quartet is not a quartet but a doublet?
No, it's still a quartet, but it's being split by something else. There's more to this molecule than this R. It's being split by something other than the groups that are being shown there. The coupling or apparent coupling is going to be affected by magnetic field because it affects the number of, or this, I guess the hertz per ppm. We've got an example. These two spectra are of the same compound, this ethyl chloroacetate. Both of them are the same compound. If you measure the distance between these peaks, you're going to get the same value for this spectrum as you will for this one in hertz. It appears that this one's narrower, but that's because this is acquired on a 7 Tesla magnet, which means it's a 300 hertz or 300 megahertz spectrometer. So between that 1 ppm, we have a total of 300 hertz. So a 30 hertz wide peak is 1/10 of a ppm. The 60 megahertz magnet, this is a 1.4 Tesla magnet, much weaker. This has 60 hertz in a 1 ppm. So if we have 10 hertz between each of these 4 peaks, that's a total width of 30 hertz. That's half a ppm. And so it can appear to be much wider because it's wider in terms of ppm, but not in hertz. Hertz is going to be constant. But this brings up another point, that as you get to stronger magnets, you get higher frequencies for it, you get less interference or less overlap of peaks. Because now that 30 hertz is just 1/10 of a ppm, we could fit more peaks inside this 1 ppm range without getting overlap. That's one reason chemists like to have more powerful magnets for NMR. The 60 megahertz was back in the old days. I actually used that originally. Those were those were electromagnets. To get the higher fields, we have to have superconducting magnets. They're a lot more expensive, but they have a lot more power as well. The one we have here in the chemistry department is a 400 megahertz, a 9.4 Tesla magnet. It's actually sort of low to mid-range these days. You can buy 600, 800, even gigahertz spectrometers. I think they've made a 1200 megahertz spectrometer now, but they're huge and expensive, and the companies making them still have difficulty getting those to work stably. All right, next one, a couple more patterns, just if you see it, should ring bells for you. One is a 9-hydrogen singlet butyl group. The other is a 6-hydrogen doublet and a 1-hydrogen septet. This would be the isopropyl. These are things you'll see somewhat frequently. One comment with the isopropyl, this assumes having your 6-hydrogen doublet that R is achiral. If R is chiral, then these methyl groups will not be equivalent, and you'll actually see 2 doublets, 2 3-hydrogen doublets. In fact, this semester you're going to be doing a Grignard reaction. You're going to have a chiral product. It's going to be a racemic mixture, but it is a chiral alcohol, and it does have an isopropyl group on it, and they show up distinct. You get diastereotopic methyl groups. So when you look at that spectrum, don't let that throw you. And now you know the reason why as well. But students often look at that and it's like, why do I have two methyl groups? It's because they're diastereotopic. If you have very different coupling constants, then you can get things like doublets of doublets, or this thing a triplet or a quartet of triplets. This occurs because we have, in this case, looks like it's hydrogen B would show up here. Because it's being split by hydrogen A, it's being split into 4. So it's being split into a quartet, basically, with a large coupling constant. So we have a large separation between each of those peaks. And then HC is splitting it again, but this time it's splitting by just a small amount. And so we're getting each of these individual peaks split into a triplet. And so this is something we'll see when we have very different coupling constants. That you'll have something like this, or the next slide shows the same thing, but now this one has the large coupling constant, and so it's being split into 3, and then these have the small one, and so each of those 3 is being split again into 4 more, and we're getting a triplet of quartets. They've got an example here of one where the coupling constants are closer, which makes it harder to recognize. This is easy to see in the one before it. It's easy to recognize that as a triplet of quartets or a quartet of triplets. I've got another example here. This is easy to see that this is a triplet of triplets, and abbreviated just a TT. And again, it's because we've got it being split into 3. And then each of those 3 is being split again. And this was done specifically with coupling constants of 10 hertz for the large coupling and 3 hertz for the smaller one. So we've got a 3 hertz separation here. We've got a 10 hertz separation there. And you can clearly see the triplets. When the coupling constants are closer, we get things like this. This is also a triplet of triplets. This one, however, if you look at that, it's not obvious. But again, we're splitting it into 3. And then each of these is being split again. And then the center one also being split to here. So we have one triplet here. We have another triplet there. And I don't, I think I can change pen colors. I'm going to do the center triplet in blue just to bring that out. But you can see each of these triplets are there. It is a triplet in that we have a 1 to 2 to 1 ratio, 1 to 2 to 1. The blue one, also, the center peak is twice the size of the outer ones. But also note the triplets, the center triplet is twice the size of the outer ones. Similar to what we have with the one over at this end here, where the 2 outer triplets are half the size of the inner triplet, and the outer peaks of each triplet are half the size of the inner one. And this, again, is a triplet of triplets. All I've done is change the coupling constant. In this case, it's 10 hertz and 5 hertz. This was 10 hertz and 7 hertz. And our triplet, in this case, because it's being split with a similar coupling constant, we have these being split like this. Actually, I think I've got this, sorry, that one should be here, not that. But being split like this, and then this one also getting the overlap. So we're having overlapping peaks, which gives rise to the funny pattern we see here. In general, when you see these other patterns, no one's going to expect you to recognize this as a triplet of triplets. And typically, when we see things like this, we simply call it a multiplet. Multiplet implies that there's many peaks. We don't know exactly what the splitting is. And for some things, if you do a lot of NMR, you'll probably come to recognize some of these. Some of them are not going to be very obvious. And sometimes you get peaks. You may have a triplet and a quartet that sit on top of each other and make it obscure as to what it is. We'll call that a multiplet as well, and simply abbreviate it M. So for this one, we should recognize triplet of triplet. The other ones, we'd simply call them multiplets. And one more comment about this. When you first look at it, the instinct might be to say, I've got 1, 2, 3, 4, 5, 6, 7 peaks. This is a septet. But remember Pascal's triangle, the septet, and this is the one I told you to keep in your back of your mind, the actual pattern is 1 to 6 to 15 to 20 to 15 to 6 to 1. This is a septet. So it has that very different intensity pattern than we have with the triplet of triplet where we get those overlaps. Okay. So, but we do get this when we have the different coupling constants, and so that can make things a bit confusing. One more point, and you've seen this if you did organic 1 here, some hydrogens don't get involved in splitting, specifically hydrogens that are on very electronegative atoms. So alcohols and amines, we often do not see splitting with that, or with those, and we can see that here in the OH peak is a singlet, and our methylene is a quartet, 3 neighbors and not the 4th one there. Okay. And that is because of exchange. The hydrogen on the alcohol can dissociate off, and then a different hydrogen from another molecule. This is showing an acid. If you've got trace amounts of acid and it doesn't take much, you could have nanomolar quantities. Even just water that's not any acid present, we can get this kind of exchange where the red hydrogen comes off and a blue hydrogen goes on. And because of that exchange, that's happening rapidly enough that any effect that the spin up, spin down might have is being negated, because you might have one on for a fraction of a second, it comes off, a different one comes on, and it gets averaged out. And so those don't show splitting. If you have scrupulously dry sample and solvent, you can actually see the splitting for that. I have seen splitting not for ethanol, but for other alcohols in the past, but it's pretty rare. Usually it's a singlet, and I've actually tried before to get splitting to show up, and unable to do it because I was not able to get things dry enough, and then just by chance at another molecule I see it. So it does happen, but it's rare. Typically, you should not expect to see it. Okay. Another compound, this is an example from the book, and again, this is predict the chemical shift, the integration splitting patterns for the protons. Step 1 again is identify what we have, and I'm going to just go back to the red. We have CH3, call that A. We have 2 hydrogens here. These are not equivalent since they're on opposite sides of a double bond. One is closer to the cyclopropane ring than the other. One's closer to methyl. And so those are definitely not going to be equivalent. So why did I put them both B? Call one of those C. We have a hydrogen here. We have 2 hydrogens here. Question is, are these equivalent? The rule is that they are equivalent unless we have a chiral center. Do we have a chiral center in this molecule? Do one of our carbons have 4 different things on it? Yeah. So, in fact, hydrogen D is on the chiral carbon, so these will be distinct. These would be E and F. Because this is a chiral carbon. It has an isopropenyl group, it has a carbonyl, it has a methylene, and it has a hydrogen. 4 different groups makes it chiral. Yes?
So that chiral carbon can be anywhere on the molecule, but it'll still affect.
Correct. Yeah. Typically, the effect will be greater on the groups closest to it. If they're far away, they may be inequivalent, but they may still show up the same chemical shift and they'll look the same, like it's just one peak because they're both sitting at exactly the same chemical shift. But sometimes it'll just be a small difference, sometimes a bigger one. Yes.
So suppose this carbon is not chiral. Just to make sure that I'm not messing this up, would those two hydrogens, not the one closest to the carbon double bond, like the carbon oxygen double bond, would it not be influenced by it?
Are we talking about the methylene group here, or are you talking about the alkene?
Here, the closest to the oxygen carbon double bond over there, the F hydrogen.
F. Yeah, E and F are distinct because it is chiral. If it wasn't chiral, E and F would be the same.
Even if it's closer to that, or no, it doesn't work that way.
Yeah, it doesn't work that way. If it's chiral, they're going to be distinct. If it's not chiral, they will be equivalent. And in fact, that brings us to this is also methylene. We also have two hydrogens here. And again, because it is a chiral molecule, these would be G and H. They would be inequivalent. And if we're also going to assign a shift in integration and splitting, now that we know what we have, we can put this in a table and start filling it in. Hydrogen A, I think I have, yes, on the next slide we have our table. So if we go to hydrogen A, this is allylic, which would be this group here. We have hydrogens next to a double bond. So this would be the 2 to 2.7 range. So roughly A would be around 2. Splitting, it has 0 hydrogens on the next carbon. The next carbon has 4 bonds to it. So splitting would be singlet, integration 3. B, this is in the vinylic range, so again we could come up here, go to vinylic, and now we're looking at this range out here, and so we would expect to find these peaks somewhere around 5, and that would be for both B and C, approximately 5. Splitting, because they are not equivalent, they are geminal, but they still split each other even though they're on the same carbon. So both of these would be doublets, 1 hydrogen. And again, I will be giving a copy of this PowerPoint to Dr. Cartias, and she'll post it. I think she posted the last one from Wednesday. D, integration is 1. This is between 2 groups. Remember, the one vinylic group would put this around 2-ish, 2 to 2.5. The fact that it's around a second one moves it up even more, so this would be closer to probably 3 ppm. And now the splitting. It's being split by 2, but because these are it's in a ring, we will probably have different splittings from these. So rather than seeing a triplet, one of them is going to split it into a doublet, and then the other one's going to split each of those peaks into 2 more. And so we would have a doublet of doublets for this one. So just to write that pattern out, we split into 2. This would be our traditional doublet, and then we would split these again, and we would have a pattern that looks more like this. And that would be a doublet of doublets. And those can be, the center ones can be close to each other. They may be closer to the outer ones, but that spacing will be there. It's a doublet of doublets. 4 peaks, equal intensity, which distinguishes it from a quartet, which would be a 1-3-3-1 pattern. Okay. E and F, next to 1 double bond, so they're not quite allylic since it's a carbonyl rather than an alkene, but they would be around 2.2, 2.3, somewhere in that range, both of them. Again, they're being split. E is being split by F and by D. Different coupling constants are expected, so doublet of doublets. Integration for 1. Next one's also 1. They only split each other, so they'd both be doublets. And again, between 2 carbonyls, we'd expect it maybe around 3.2 or so, both. So we'd expect something like this. The exact chemical shift you're not going to have, but you'd know the general region. This is a simulated spectrum. This isn't the actual one. This is a simulated, but it gives you an idea of what we'd be looking at. And as I mentioned, these are doublets. So we have our 2 doublets down here. These are the doublet of doublets that we're looking at. And again, it depends on the splitting as to whether we have doublet of doublets that look like this or more like this, or something like I drew before where they're more or less evenly spaced. But we'd have something of that sort. NMR does help us to distinguish sometimes between isomers. If we look at these dimethyl benzenes, center, we have this a mirror plane or an axis of rotation, meaning the left and right halves are going to be equivalent. So this is A, this would be A. B, B, C, C. So we would expect 3 signals in this. Likewise, with this one, 2 methyl groups are going to be equivalent because they're basically mirror images of one another, or we have that axis of rotation. You could use either way, B's. And then the 2 hydrogens on that axis are going to be distinct. The green one is closer to the 2 methyl groups, whereas the other one is closer to 2 hydrogens, so they're definitely not equivalent to each other. So we would expect to have 4 signals. And so, same thing here. AA, BB, but this one actually has one more axis of rotation or mirror plane, whatever you want to use. This down here. If we rotate around that axis, the top and the bottom can replace each other. So the top halves and bottom halves are equivalent as well. So if the top 2 are A's, the bottom 2 are A's. So we would have only 2 signals. All 4 aromatic hydrogens are equivalent, and then the 2 methyl groups are equivalent. And so NMR can be used in that way when we think about just the number of signals that we would expect in something. All right. Last thing we'll do is look at an example where we are taking NMR data and trying to get a structure. So rather than predict the spectrum, more commonly what you're going to do is get a spectrum and you have to predict the structure, determine what this is a compound of. If you have a formula, you can calculate, oops, I meant to do that on the previous slide. Where was it? Here it is. Calculate the index of hydrogen deficiency, or they call it hydrogen deficiency index. We have a formula, 7 carbons. Remember, fully saturated, we have 2N plus 2 hydrogens. So we would expect to have 14 plus 2 hydrogens. We expect to have a total of 16. Each nitrogen could add 1 more, but no hydrogens, excuse me, no nitrogens. So we would expect fully saturated, no rings, no double bonds, we would have a total of 16 hydrogens. Subtract the number that we do have. 13 gives us 3, except each halogen replaces a hydrogen, so subtract 1 for each halogen, we have a chlorine. Means we are 2 hydrogens short of fully saturated. And since each ring or double bond removes 2, we divide by 2, IHD of 1, meaning we have either 1 double bond or 1 ring in our structure. So we've got a little bit of information that we can use. The next step then is to actually go through and interpret what we have. My recommendation is start with integrals, look at the pieces, draw them, and you can use chemical shift to help along the way, and then put it all together with the splitting. So we have 5.3, a doublet of quartets. Again, go to our table. 5.3, this is in the vanillic range. So that tells us we have a hydrogen on a carbon that's part of a double bond. And carbons have 4 bonds, so I'll draw them in there. 5.1 is the same region, so we have another one of those. 3.4, if we come back to our table, we're looking in this range. This is where we have the CH, where the carbon is bonded to an electronegative atom, such as hydrogen or chlorine. In this case, we know we have chlorine. So this would be our CH from the integration of 2 hydrogens. This is CH2. And from the shift, we know it's bonded to chlorine. Then we have a doublet, integrates to 3 hydrogens at 2. This is a methyl. And then we have one more peak, a singlet, 6 hydrogens out at 1 ppm. So we have what, a CH6? Nope. What do we have? Probably 2 methyls. So these are the pieces in our molecule. Question is, how do we put them together? Of course, another question is, do we have everything? If we start adding this up, got 3, 6, 9, 11, 12, 13 hydrogens. Looks good. 1, 2, 3, 4, 5, 6 carbons. We're missing one. One of our carbons obviously does not have hydrogen on it, since it's not showing up in the proton NMR spectrum. So we must also have a carbon, of course 4 bonds, but no hydrogens attached to it. Question then is, how do we put this together? Obviously, the 2 vanillic ones are going to be bonded to each other. So we've got a double bond. I'm going to redraw that. So we've got this. Whether it's cis or trans, we don't know, but we're going to leave it in the cis for the moment. I'll also draw out the trans one. And then what's bonded to these? The one at 5.3, doublet of quartets. So the doublet tells us it's got a 1 hydrogen neighbor. That would be this one here. It also has a quartet splitting, which means it has, this other carbon must have 3 hydrogens on it to account for a quartet. We've got 3 methyls, so one of those is bonded there. Which one? Again, we can look at our splitting, excuse me, in this case, chemical shift. We have one of these shows up at 2 ppm. Again, if we go back to our table, 2 ppm is where we see allylic, things next to a double bond. So that tells us that this methyl is bonded here. All right, what about this other carbon? This one here, our table tells us, or our data line tells us we have 1 hydrogen. It's a doublet. Doublet would account for this neighbor here, meaning this carbon has no hydrogens. If it had a hydrogen, it would also contribute to the splitting. So this must be our quaternary carbon. So we can take it out of play. Our chloromethyl group, this one here, is a singlet. So that tells us it also is bonded to a carbon with no hydrogens. So we can bond this one up here. And then our 2 methyls must be bonded down here. And in fact, if we look at the splitting, both of those methyls are singlets, which tells us that they too must be bonded to a carbon that has no hydrogens. And the fact that they're on the same carbon and we don't have a chiral center also would account for the fact that there's a single peak. These 2 methyl groups are equivalent. And that's why we have a single peak that integrates to 6 hydrogens. And as I mentioned, we don't really know for sure if that's the cis or the trans. We could have this as well. And it would depend then on the coupling constant. As a general rule, coupling constants for cis alkenes, so we're talking specifically about these, the J value is going to be at about 10 to 13 hertz. For the trans, it's typically in the range of about 14 to 18 hertz. So you can tell the difference if you can measure the coupling constants. This is something that you'll be doing in lab in about 3 weeks, I think, a couple of weeks. When you're doing the Wittig reaction, second week you're going to be analyzing the spectrum and you're making an alkene and you want to determine is it cis or trans. Okay. So spectrum for that, the reason I think they gave the data line is the fact that this is a peak that's not easily discernible as a doublet of quartets. All right. Any questions? All right. It's a lot there, a lot to digest. My suggestion is work practice problems, especially doing interpretation, just to get a feel for it. And if you do lots of practice problems, you will, in time, also learn the areas, the regions where you see them. You know, this is aromatic, this is vanillic, this is the alkoxy, this is allylic, and this is alkyl. But if you do a lot of that and keep looking at the table, those will become second nature to you. Have a good weekend.